Welcome to Mrs. Mahoney's podcast. This is our fourth one in our Unit 7. We are looking at page 13 in our Unit 7 packet, and we're going to start looking at some of the same reactions. We're not changing the reactions, we're just kind of looking at it from a different viewpoint. Now I know we've looked at double replacement reactions and called them precipitation reactions, another name for them. Now we're going to look at some of the other ones and realize that they can go under another name also, and it's a lot more general, and we'll find out that actually synthesis, decomposition, single replacement, even combustion will all fall under this redox name. So we're going to look a little bit more into what does this redox really stand for. So we're at the top of page 13. We're just going to fill in some notes and do some practicing. So we're going to get to where tomorrow we can practice balancing some of these, and we're going to balance them in a little bit different way that we realize we have to focus more on maybe on what's happening with the electrons and not just the atoms. So starting at the page 13 here, let's just kind of look at what we're talking about. So what is this redox reaction? It's a word that we just kind of throw out, and it's a shortened word, and it stands for oxidation reduction. Or I guess we should technically reverse that, reduction-oxidation reaction. So that's where the redox comes from. Well, what a redox is when we actually get a movement or a transfer of electrons, and that's happening between different atoms and different ions. So we're going to start assigning oxidation numbers. Well, we can look at this, and what is an oxidation number? Try and put this in a color we can see. An oxidation number, the majority of the time, sorry, a little bit of syllable there, the majority of the time is its charge. Unfortunately, I can't say 100% of the time it's going to be the charge. If it's by itself, it's the charge. Sometimes, and it's really some of those covalents, we're going to realize it's really going to be a little bit different, because what the oxidation number really is going to be representing is where the electrons are in a compound. Who is getting their share of the electrons in a compound? So what we're going to have to start doing then, the first thing we need to do then is to realize where do these oxidation numbers come from. So once we assign that, we will then classify a redox reaction is when we see a change in these oxidation numbers. And again, these oxidation numbers, the majority of the time is the charge, but we do have to focus a little bit on when it is not as easy as their charge. So you have this in your chart, but there's a huge mistake in your notes. So I need you all, okay, right here, so let's start at the beginning. An uncombined element, okay, this is just saying if you have any neutral element, here's some examples, that the oxidation number is just 0. Okay, if it's just an ion, and what you're going to start seeing is we're going to start doing some net ionic equation, which means I'm going to kind of cut out the garbage and let's just really focus on what's happening. So if you see something that has this would just be its charge. Silver would have an oxidation number of 1, chloride -1, and this again would be a positive 1. Sulfur -2, this copper would be a +2. Those are the easy ones. Okay, then we're going to have to start looking at some of the rules. Oxygen is pretty much going to always be a -2 unless it was in some kind of peroxide. Now remember, the only time you'd really see a peroxide would be if it's a group 1 metal peroxide or this hydrogen peroxide. Another thing I want you to write down, fluorine, since we know fluorine is the most electronegative element, write another note, fluorine in a compound is always the -1. Fluorine kind of trumps everything else. So the only time actually that oxygen might change its oxidation number is if it's in a compound with fluorine. Fluorine is the most electronegative, therefore fluorine would always get the negative charge. Again, this negative means it's taking more than its share of electrons. Okay, this is where your mistake is at, right here. I have changed it on my PowerPoint, so look at your notes. These are switched. Hydrogen in most compounds is a positive one, not the negative one that you have. Make that change. So in all of these, I would assign hydrogen a positive 1 charge. The really only time that hydrogen is a negative 1 is if it's combined with something that is not as electronegative, which means when it's with a metal. So in a metal, again, I'll never give a metal a negative. So since I'm never going to give a metal a negative, that means when hydrogen is with a metal, it's going to be assigned then a negative charge. So let's kind of look at as practice assigning some of these numbers. So this is your work right here, and it's like, okay, let's assign some of these numbers. So look at oxygen right here. It's a neutral element, and when I assign oxidation numbers, I just kind of write them right above them. So it's a neutral element. That means this would have an oxidation number of 0. It's not it doesn't have to worry about who's taking more than its share. Everything is being shared evenly. Okay, let's look at right here. So in this nitrogen, okay, we go back up to our rules. Hydrogen, we said, is always a +1. Okay, this is where we're going to have to do some of that mental math. And when we add it up, let's go back right up here. Kind of skipped over this. This is really, really important, so I shouldn't have skipped over it. When I add up the oxidation numbers, if it's a neutral compound, the oxidation numbers of all the elements have to add up to 0. If it's some kind of an ion, if I add up their oxidation numbers, the oxidation numbers have to add up to the charge. Okay, so look at this. There was no charge. It was neutral. That's why this has an oxidation number of 0. Okay, this is a compound. So this is saying I have each hydrogen has a +1. Well, look at I have 3 hydrogens. So that means if I was kind of down here, this is what we can get to where we're doing it in our head, but I'll write it for now. This means the total oxidation charge from hydrogen is a +3. Well, it has to add up to 0, kind of like an ionic compound. So that means the oxidation number in nitrogen is a -3. Okay, that is the same as the charge, not a big deal right now. Okay, let's look at the chloride. Again, assign the metals really aren't going to change, and the most electronegative is going to be its charge. Okay, that's a -1. That means copper's a +2. Okay, that's not different from its charge. That's not going to change. In ionic compounds, it's not going to change. Okay, let's look at here. Hydrogen is a +1. Now, when we're adding this, though, this means there's 4 of them, so this is a +4. Okay, now look at right here. This has an ammonium. This has a charge of +4. So that means when I add all of these together, it has to add up to that +4. So the only way to get that would be if nitrogen is still a -3, because -3 plus a -4 equals -3 plus a +4 equals a +1. So it adds up to that oxidation number. Okay, this is where it starts to get a little bit weird. Okay, so look at N2O. Well, oxygen is the most electronegative. Oxygen is always at -2 because it's not with fluorine, not a peroxide. Those exceptions you're really not going to see very often. So this is where nitrogen can actually change the oxidation number. This is where it's different than its charge that we're looking at in an ionic compound. So what I know then is if I add this all together, it has to equal 0. Well, there's 2 nitrogens. So that must mean each nitrogen is a +1, because 2 times a +1 is a +2, +2 plus a -2 equals 0. So in this compound, nitrogen is a +1 versus what we're used to in the charges of being a -3. What does that mean? That means in this compound, oxygen is taking more than its share of electrons. That's what that -2 oxidation number means, who's getting their share. So the higher the negative number is, the more electrons, because electrons are negative. Okay, chloride, well, it's a -1, it's a chloride ion, so that means its oxidation number is just a -1, the same as its charge. Okay, this is a metal. Chloride is a -1. That means this iron must be a what? +2. Okay, look at right here. Easy. These are the easy ones. What is this? +2. Calcium. Element. Pure element. Pure elements, 0. Okay, let's look at this one. So if I'm looking at this one, this has to, when I add all the numbers, this is one of the ones where it says it's going to have to add up to its charge. So its charge is a -2. Well, oxygen is still -2. Okay, but there's 4 of them. So in my head, I'm saying, okay, well, -2 times 4, I know that this is a -8 is coming from my oxygen. So -8, but whatever sulfur is added to this -8 still has to add up to a -6. So what's the sulfur missing charge? Oxidation number plus 6. Okay, and again, we can kind of look on this one. Sulfate, again, you know what? In a polyatomic ion, when I know its charges, it's not going to change. But let's do the math to kind of show how I know this also with a compound. -2, that's a -8 down here. Well, I know calcium is always going to be a +2. Your metals aren't going to change. Okay, again, if it's a group 1 or group 2, the metals that change are the transition metals. So look at what's missing. It all has to be a neutral compound. So what is sulfur? +6, the same as in the sulfate. 2 ways you can do when you have a polyatomic ion. You can just kind of look at what the polyatomic ion is by itself, or go ahead and do all the math of it together. One last one I'm going to do, and then I'm going to have you work on these, and we'll do them together in class. Okay, how do I do this? Do the ones I know. Oxygen is always a -2. Hydrogen is a +1. Then do the missing one. These are my consistents, that's why they're in the chart. So what does that mean that the chloride is that's missing? It's going to be the +1. Okay, these we're going to kind of get back together, and we're going to pick tomorrow, try some of these, and this is where I'm going to kind of pick up before we start trying to balance the equations. Okay, so now what makes it a redox reactions? We have to look at what happens with the electrons. So there's a couple sayings. So if an element has lost electrons, what you're going to see is that oxidation number is going to increase because it's losing a negative. If it loses the negative, the oxidation number becomes more positive. That whole opposite thing is back. So if that happens, we say it's been oxidized. Okay, there's 2 different sayings we have to kind of look at this. We can either say oxidizing is losing. Okay, oil will go with rig. Leo, the lion, goes with ger. These are 2 sayings. If they help you, use them. You don't like them, forget them. And again, I wouldn't try to remember all of them. It's just oil rig or Leo says ger. So the first one for oil rig is oxidation is losing. And when I'm talking about losing, what I'm talking about is electrons. You may want to add that, electrons. So then the second part, losing electrons, is oxidation. Again, whatever you're going to say. So let's look at the opposite. What if an element has gained electrons? That means you're going to see a decrease, or the oxidation number is going to get more negative. When I say a decrease, it's going to become more negative because it's gaining negative electrons. If that happens, we say it's been reduced. And the saying then, we had oxidation is losing. What goes with that is oil rig. Reduction is gaining. So those are the 2 that go together. If you want to look at the animal, Leo goes ger. So we had losing electrons is oxidation. So then gaining electrons is reduction. And it's just how you classify. It's all about really classifying a reaction and recognizing if an element, we will start to say, has this element been oxidized or has it been reduced? How do I know? I look at its charge. What has happened to the charge is how I classify it as either a reduction or an oxidation. Okay, so let's look on your sheet and kind of look at what we're even talking about. Now, in a lot of these reactions we start looking at, we're only going to look at one element at a time and start calling them half reactions. That might bother some of you, and you're like, well, looking at this example, you might say, what happened to the chlorine? What's going on with the chlorine? Okay, we're not worrying about the chlorine at this point, and it's okay to ignore some of the things that are actually happening in part of the times. So I'm just looking purely at the copper right now. So look at over here on the right hand side. This is an elemental copper, so it's just a 0. Look at over here. This is a -1, so this copper is a +2. So you're like, what happened to your numbers? The number, it got more positive. When it got more positive, that meant that this actually lost electrons. That's how it went to a negative charge. So we would say then copper has been oxidized because it lost electrons. Okay, look at our other example then. Look at the silver. What happened with the silver? Silver went from in this, it was a +1, and then over here, it is a 0 because it's just the elemental silver. Look what happened to your oxidation number. It decreased. And why is that? Because it gained a negative electron. So we say that silver has been reduced because it gained electrons to get back to that elemental state. This is a redox reaction, is when you see a change in the reactions. Okay, so let's look at a couple more of them. Down here, we're just going to kind of analyze some of these of what's happening. And again, right now, we're not balancing the atoms. For now, we're doing that tomorrow. Purely, I'm looking at, let's assign some numbers. And to do these, I really put the numbers above them. So this is what, a 0. Chlorine, I know, is a -1. That means this copper is a +2. Over here, 0. Those are my easy ones. Chlorine, -1. A zinc, a +2. So look at chlorines. Did nothing. I don't care about those then. I'm going to totally ignore those. So what happened? Zinc went from a 0 to a +2. Okay, sometimes it helps to think of like a number line. Think of just a number line. 0, +1, +2, +3. When you see an increase in the number, we say it's been oxidized. I'm going to run off. Okay, so when you see the opposite then, when you see a decrease, or you see the oxidation number decrease, that is when it has been reduced. So zinc went from a 0 to a +2. We say zinc has been oxidized. What else changed? Copper went from a +2 to a 0. So look at copper went from a +2 to a 0. That number was reduced. If the oxidation number is reduced, we can say that the element was reduced. So copper was reduced and zinc was oxidized. One thing about a redox reaction, you can never have just half of that happen. If something is oxidized, something else has to be reduced. It's a transfer, a movement of electrons. Okay, look at this. So this is a single replacement. So single replacements are redox. Okay, look at this. This is a synthesis. Well, these are 0, zeros. Magnesium over here is a +2. Oxygen is a -2. Notice I'm not worrying about the balancing or anything. I'm just looking at charges or oxidation. What happened? Magnesium, 0 to a +2. That means magnesium was oxidized. Oxygen went from a 0 to a -2, became more negative. How did it become more negative? It gained electrons. If it gained electrons, that meant it was oxidized. Okay, over here, decomposition. So synthesis or redox. Okay, this is a decomposition. In the compound, -2 for oxygen, +1 for hydrogen. But over here, in the elements, they're both zeros. Hydrogen went from a +1 to a 0. So how did it go from a +1 to a 0? It gained. So over here, hydrogen was reduced. Oxygen went from a -2 to a 0. -2 to 0, the oxidation number increased. Oxygen was oxidized. Okay, so single replacement, redox. Synthesis, redox. Decomposition, redox. Okay, what's this? This is a double replacement. Okay, aluminum +3, chloride -1, iodide -1, sodium +1, chloride -1, sodium +1, iodide -1, aluminum +1. What changed? Nothing. Nothing changed. Nothing changed. Nothing. Nothing. This is not a redox. Therefore, Double replacement reactions are not redox reactions. You do not see a change in their charge, therefore they are not a redox reaction. Okay, we're going to start up with this tomorrow, going back over this. We're going to work on it the whole day tomorrow, spent in asking some questions, and we're going to kind of realize we're going to balance these a little bit different ways when we have to kind of balance where those electrons will go. I will see you tomorrow.